So let's begin. Welcome everyone. Welcome to the virtual lab in chemical engineering class. So this is our ninth lecture in this series, where previously we saw experiments related to fluid flow operation, and then we started with the heat transfer experiment laboratory, right? Now we have seen heat transfer through conduction and heat transfer through convection in last two lectures, right? So today we will move forward with the same idea, and then we will look for the third mode of heat transfer, which is radiation. So we will do experiment related to heat transfer in radiation, where we will be computing emissivity of different materials, right? So first I will be discussing theory behind the heat transfer through radiation, and then we will discuss the analogy of experiment, what we will do, then we will perform the experiment in the virtual lab. Okay, so let's begin today's class. So aim of our experiment is to compare the heat transfer between different material surfaces and black body surface through radiation, and to find the emissivity of different materials that we will use in our experiment. Okay, I have already discussed this part previously also, that the three mode of heat transfers are conduction, convection and radiation. I am not going to discuss about the conduction and convection today. We have already discussed in previous lectures also. We will be focusing on the radiation part, right? Now any body or any material above absolute zero temperature, above 0 Kelvin temperature, will emit some amount of radiation through itself, right? So that radiation helps to transfer heat through electromagnetic wave. So heat in the radiation is transferred by a movement of electromagnetic waves from hot body to its surrounding, right? So thus does not require any medium for heat transfer. In conduction and convection, we saw that we need a physical media for a heat to transfer, right? But in radiation, since these are the electromagnetic waves emitted by a body, so thus radiation does not require any medium. As a chemical engineer, whatever radiation that we deal with is mostly thermal radiation, where the infrared spectrum radiation plays an important role, right? So apart from that, there could be radiation in different spectrum. I mean, these are electromagnetic waves, right? So depending upon the wavelength, you can differentiate in different spectrums. You have visible light spectrum, you have ultraviolet light spectrum, and the infrared spectrum. So all the thermal radiation stuff that we deal as a chemical engineer in furnaces are related to the radiation through infrared spectrum. So now we know that, okay, any body which is above the absolute zero temperature emits some sort of a radiation, but then how to compute that radiation? So that is given by this Stefan-Boltzmann law, which says that the energy emitted by a body per unit time, per unit area, is proportional to temperature to the power 4. So heat flux emitted by the body through radiation to its surrounding is proportional to its absolute temperature in Kelvin to the power 4, right? Now if we remove the proportionality constant, so then we will add a proportionality constant. So heat flux will become sigma into temperature to the power 4, where this sigma is your Stefan-Boltzmann constant, and its value is 5.67 into 10 to the power minus 8 watt per meter square per Kelvin raised to 4, right? So it was given by both the scientists, Stephens and Boltzmann, right? So it's called as Stephen-Boltzmann law. Now, if we look at the analogy of conduction and convection, in conduction, we saw that heat flux is proportional to temperature gradient. In convection, heat flux was proportional to the difference between the temperature of two fluids or two material, right? So here we got a proportionality constant as a thermal conductivity and here heat transfer coefficient. But in both the cases, heat transfer is proportional to temperature to the power 1, while in the radiation, the heat flux is proportional to 10 to the power 4. That means as temperature of body will increase, energy emitted through radiation by that body will increase much faster, since the power law is followed and we have power of 4, right? So if I consider an body number 1 which is at 1000 Kelvin, then the second body which is, let's say, at a room temperature of 295 Kelvin, right? So if you will look at Q1 will be 1000 to the power 4 into Stephen-Boltzmann constant, Q2 will be 295 to the power 4. So if you take a ratio, you can understand yourself that the energy emitted by same material at 295 Kelvin and at 1000 Kelvin will be much higher in magnitude. Okay. So that is the uniqueness about the radiation, that the energy emitted is it's proportional to the fourth power of temperature. Now this equation that I have provided is considering that the energy emitted is by an ideal black body. Now what is ideal black body, we will come to that also, but for a real world material or real world body, if we consider, then there will be some deviation from ideality. To address that, another constant, emissivity, is added, emissivity of material of the body, right? So in that case, heat flux becomes emissivity into Stephen-Boltzmann constant into temperature to the power 4, right? Now here, what this constant means and what is this emissivity and what is this black body, let's try to understand that. So as I said, that radiation is possible because any body which is above absolute zero temperature will emit some sort of a radiation in all direction across different wavelengths, right? And it's possible, like this emission is possible in all direction. Okay, the amount of the radiation that will be emitted, which spectrum it will emit, it will depend upon the material property of the body and nature of the surface. So how its surface is and what kind of material we have. Now black body is an idealized state matter which absorbs all sort of radiation that are emitted on itself, and it will also emit maximum amount of radiation within itself. Okay, so if I have a black body and there are radiation energy incident upon it, then it will absorb all this energy, all this radiation. At the same time, this black body will emit some sort of a radiation based on the amount will be based on the Stephen-Boltzmann equation, right? So a black body or an ideal radiator is body that emits and absorbs at any temperature the maximum possible radiation at a given wavelength. So that's the definition of a black body. Okay, so it's an idealized state. Now these are the features of a black body, that a black body emits more radiation energy at a specified temperature and wavelength than a real one. So real body will emit less amount of radiation. Black body absorbs all the incident radiation regardless of its wavelength and direction. It emits radiation energy uniformly in all direction. Thus the black body is uniform diffuse emitter. So this means that emission is independent of any direction. So thus black body is an diffuse emitter. So it's an ideal state. Now if we talk about the real body, so real body will emit, so our real body emits less energy compared to black body. Okay, so if we take the ratio, if I have a real body, if I have an ideal black body at the same temperature, having a same property, similar kind of a property, then energy emitted by radiation energy emitted by the real body to the energy that will be emitted by a black body, that ratio is called as emissivity of a surface, right? So emissivity, its symbol is E. Its ratio of energy emitted by real body to energy emitted by black body. Okay, now depending upon type of surface, this part, I will come to this part also. So this is emissivity part. Now in emissivity also there are different types of emissivity that we can categorize. So let me show you that also. So one is total emissivity, which is eta, that we saw, which is a ratio of energy emitted by real body to the black body. Then you have spectral emissivity, which is given as E lambda. So it's ratio of radiation emitted by real to black body with wavelength lambda, right? So if you want to specifically look at the sum spectrum and then analyze, okay, how much energy is emitted by this body in this spectrum, so then you can use the spectral diffusivity. Apart from that, we have directional diffusivity also, directional emissivity, which is kind of related to directional diffusivity. So here we saw that an black body is a diffuse emitter. Okay, so it will emit energy in all direction, but if the real body will deviate from the ideal black body, then we might have directional emissivity for that body also. So this all has some sort of application that we will come upon. So this is how the concept of emissivity came. We are comparing the real world material with the ideal black material. Okay, so thus if you use emissivity, Stefan-Boltzmann constant, if you know, that is already known. If emissivity of material is known, then we can find amount of radiation energy that will be emitted by that body at a given temperature T. Now let's consider an example of this metal surface where some incident radiation is given to the surface, right? Now depending upon what kind of material we have, it might absorb this part of this energy, it might reflect part of this energy, and it might allow this part of this energy to transmit through itself. So we have these three terms, which are absorptivity alpha, then transmit, which is equal to tau, and you have reflectivity, which has a kind of eta symbol. Okay, so if any radiation is incident upon on the surface, what will happen to that radiation will be determined by this value of this 3 fraction. So for any material, summation of this 3 will be 1. Okay, so if we consider an ideal black body example, it absorbs all radiation energy incident upon itself. So for a black body, alpha will be 1, right? If you consider an opaque surface, opaque body, that means it does not allow any light to pass through itself, then in that case transmission will be 0. So you will have absorption plus reflection equal to 1, right? So that is your an opaque surface. Now there is another concept which is known as the Kirchhoff's law, which says that under thermal equilibrium, the emissivity of a body is equal to its absorptivity. That means alpha is equal to emissivity. So in Kirchhoff's law, insert new slide. Yeah. So you have Kirchhoff's law, which says at thermal equilibrium, absorptivity will be equal to emissivity, which in a way denotes that at equilibrium, total energy taken in by a material will be total energy put out through radiation by same material, right? So this is a Kirchhoff's law. How it is useful, like it helps us to interpret that good emitters, if you will consider, good emitters are also good absorbers. So for example, black paint is considered as a closer approximation to the black body, so it's a good emitter. So thus it also becomes a good absorber, so it will absorb all the energy incident upon itself, right? Similarly, poor emitters are poor absorbers. So example for this, you can consider any shiny metal, right? So they will emit radiation poorly, thus they will also absorb radiation poorly. So emissivity value of 0.9 to 0.98 is observed for black body like black paint. We get the emissivity value of somewhere around 0.1 to 0.3 for polished metal. Okay. So then you can understand how much amount, like since they emit less radiation, they will absorb also the less radiation, right? So now what happens, that here this is done. How it is useful? It is useful in the sense that, let's say if I want to select some material to reduce the heat loss in my furnace area. Okay, so usefulness will be, let's say I have low emissivity for any material, so this will reduce the heat loss through radiation. So example will be reducing the energy loss, radiation loss in furnace surrounding. Then the some spacecraft blanket are also made of material which has a lower emissivity to preserve the energy, so that energy loss through radiation is less. Then let's say if you have a high emissivity material, so that will have a improve heat transfer through radiation. So cases where you want to increase the heat transfer through radiation, then you can select a material with a higher emissivity. So mostly inside of the furnace, where furnace tube we want to have a material which absorbs all the radiation energy, right? So you can consider that example. Then another example you can think about is infrared thermophotography, right? So in this case what happens, that this IR camera, they take a heat map, right? So that the emissivity value is needed to calibrate this IR cameras. Then solar panels also, solar panel also rely on the idea of emissivity of a material, right? And you can consider this as an example of spectral emissivity. Okay. So here what happens, that in solar panel our aim is that panel should absorb most of the visible light that is incident upon it, so like most of the visible sunlight, while it should also emit less amount of infrared light. Okay, so we want to maximize absorption of visible light and minimize emission of infrared, okay, to minimize the loss. So this is an example of spectral emissivity. Okay, so if you want to design best solar panel, you should work somewhere around material which has some sort of this property, right? So this were the example of how this emissivity or absorptivity or transmission or reflection is useful for a given material. Now the aim of our experiment today is to compute the emissivity of a given material, right? So how to do that? For that we will discuss the experiment setup. Before that, let's consider an example where we want to compare the energy transmission between black body and a real body. So let's say you have two plates, plate number 1, plate number 2. This is a black body and this is a real body, right? So there will be radiation emitted by body 1. Part of this radiation will be incident upon the body number 2. Similarly, body number 2 will emit radiation, part of which will go to body number 1. Okay. So, energy emitted by body 1, not A, sorry, let's say Q1, will be epsilon 1 sigma into T1 raised to 4, right? Now, since it's a black body, this value will be 1, therefore Q1 becomes sigma T1 raised to 4. Similarly, Q2 we can write emissivity of material number 2 and temperature to the power 4. Now, this much energy is emitted by body number 1, part of which will go to the second surface. Since they are both parallel, energy emitted from the surface 1 will directly go to the surface 2, since they are in parallel alignment, right? Therefore, energy balance for surface 2 will look like Q total is, first the energy that is incident upon the from body 1 to body 2, so that will be alpha 2 times sigma into T1 raised to 4. Why alpha 2? See, because this is the total energy Q1 emitted from body 1 to body 2, but body 2 might not be able to absorb all of it. How much it will absorb, that will depend upon its absorptivity, so that's why alpha 2. Then body 2 itself is also emitting an energy as eta 2 sigma T2 raised to 4. Now, at thermal equilibrium, Kirchhoff's law says that both emissivity and absorptivity of a material will be equal. Therefore, we can write it this as Q. Sigma also we can take out, right? T1 raised to 4 minus T2 raised to 4. So this is an heat transfer balance through radiation for body number 2, right? Where part of the black body energy is absorbed and some amount is emitted through itself, right? So this is how you do the energy balance. Now here, one thing that we have considered, that both body are parallel to each other, right? So energy emitted from body 1 will go to body 2, body 2 will go to the body 1, right? So we have only included the the emissivity factor. But let's say if this two plate, they were placed parallel to each other, right? In that case, if energy is emitted by body 1, so since they are not directly related to each other, the part of the energy emitted from body 1 might not go to the body 2, right? So depending upon how these two materials are faced to each other, then shape factor also plays an important role here. So for that, there is this term which is called as view factor. So view factor is given by energy transmitted by body 1 and incident on body 2 to the total energy, not transmitted, I will use a emitted word just to avoid any confusion. Total energy emitted by body 1, right? So this is called as view factor from body 1 to 2. This shows that if body 1 emits, let's say, X amount of energy, how much of that X amount will be it directly incident upon by the body 2. Okay, so then after body 2, whether it will absorb this energy, will it reflect back, that is a different story. But how much of that energy is incident upon this second surface, that will be determined by based on the view factor. So since in this case the two body are parallel, view factor is 1. Okay, else if they were at some different angle, in that case f12 will be this f12 will be between 0 and 1, right? Its value will be, so in that case its value might be, let's say, 0.5. That means total energy emitted from body 1, only 0.5% of it will be used by the body number 2. So here fraction of you might have to add fraction of 0.1 f12 along with your equations, right? So that is an important aspect to consider. Since for this example we don't have to worry about it, maybe in the next lecture we can consider more example of view factors, right? Now to measure the emissivity, what our experiment setup is that, excuse me, yeah. So our experiment setup contains a chamber in which one black body and one real body is placed. So it's a we have a black body and this is your real body. So they are placed parallel to sideways to each other, right? And they are kept at constant heating through heater. So let's say the temperature of black body becomes TB after equilibrium. This is your sample, so that is TS, and the surrounding is at temperature, the chamber is at temperature TC. Okay. Now if you will do the energy balance for black body and the sample itself, then QP will become energy emitted out by this black body will be epsilon B black body into sigma into TB raised to 4. Now this is the energy emitted. It might, so here I am just avoiding the sign, like previously I considered incident radiant energy as positive and emitted energy as a negative. I am considering reverse now. So this much energy is emitted. Now it will also absorb some of the energy which is provided from its surrounding, right? So that will depend. So that will be TB into chamber raised to 4, right? It will be alpha B. Since at equilibrium alpha emissivity and absorptivity will be same, so you can write it as TB raised to 4 minus TC raised to 4. This is QB. Same for sample also we can write E sample TS raised to 4 minus TC raised to 4. Now here, since these two plates are parallel to each other and the radiation energy is going this way, the chances of direct incidence of energy emitted from body 1, like black body to the sample body or sample body to the black body, will be close to 0. Okay, so that's why we have not considered the energy exchange between black body to real body here, but rather energy exchange is occurring via its chamber. So black body, let's say black body emits some energy, it goes to the chambers absorb part of that energy, and it emits and reflect back some energy. Then it goes to the real body, body will absorb part of it. Same way, other way around, right? So overall heat exchange is happening between both QS, black body, and the real body, black body and the sample. But it's not occurring directly, it's occurring through the chamber media, right? So at the end, at equilibrium, both QS and QB will be same. So in that case, we can write this. Therefore, if I want to compute emissivity of a sample, then I can write it as TB raised to 4 minus TC raised to 4 TS raised to 4 minus TC raised to 4, right? So this is how we compute emissivity of a given sample, that we put it close to a black body in a chamber, and then we compare the we allow steady state to attain. Both the plates are heated at the same temperature, same heating rate, and then we compare the energy exchange between both the bodies and then compute the emissivity. Now for a black body, obviously we don't have since black body is an idealization, we don't have actual black body, but we will consider the closest approximation. So this material is painted with the black coating so that it behaves similar to the black body. Okay, so this is our idea of an experiment to compute the emissivity. So what we will do now, we will go through the experiment part, where first we will look at the actual experiment in the real world, then we will move to the simulation and find the emissivity for some materials. Okay, now to do though, let me share my screen here. And this I can stop. Okay, so let's first look at the example of actual experiment setup, how it will look like.
Heat transfer by radiation. Aim. To compare the heat transfer between different material surfaces and the black body surface through radiation, and also to find the emissivity of different material surface. Apparatus. Emissivity measurement apparatus. The experimental setup consists of two circular aluminum plates, identical in size and provided with the heater coils at the bottom. It is kept in an enclosure so as to provide undisturbed natural convection surroundings. The heat input to the heaters is varied by two regulators and is measured by an ammeter and voltmeter. Each plate has 3 thermocouples. There is a thermocouple in the enclosure to read the chamber temperature. One plate is an idealized black surface, which is blackened by a layer of enamel black paint, and the other plate is a test plate. Theory. In radiation, energy is carried by the electromagnetic waves emitted by every object. A black body or ideal radiator is a body that emits and absorbs at any temperature for a given wavelength. A black body exhibits following features such as it emits more radiation energy than the real one at a specified temperature and wavelength, absorbs all incident radiation regardless of wavelength and direction, and emits radiation energy uniformly in all directions. That is, a black body is a diffuse emitter. Emissivity of a surface is defined as the ratio of the radiation emitted by the surface to the radiation emitted by the black body at the same temperature. If a sample is replaced by a black body of temperature of same area at same temperature under thermal equilibrium, the emissivity of the body is equal to the absorptivity. The ratio of emissive power of a body to the emissive power of a black body is called emissivity. Heat emitted by the black body QB is equal to epsilon B TB raised to 4 minus TC raised to 4. Heat emitted by the test plate QP is equal to epsilon P sigma TP raised to 4 minus TC raised to 4, where epsilon B is the emissivity of the black plate, epsilon P is the emissivity of the test plate, sigma is Stephens-Boltzmann constant, that is 5.67 into 10 raised to minus 8 watts, meter raised to minus 2, Kelvin raised to minus 4. TB is black body temperature in Kelvin, TC is the chamber temperature in Kelvin, TP is a test plate temperature in Kelvin. Since input power to the two test plates is same and conduction heat laws are also same, QB is equal to QP. Emissivity. Epsilon P is equal to epsilon B, TB raised to 4 minus TC raised to 4, the whole divided by TP raised to 4 minus TC raised to 4. Procedure. Power on the switch. There is white knob that can be used to turn on and thereby apply power either to the black plate or specimen plates. The white knob can help fix a voltage and corresponding current for both the black plate and specimen plate. After the steady state is reached, the temperature T1, T2, T3, T4, T5, T6 and T7 of the thermocouples are noted in the temperature indicator. The experiment is repeated for different values of voltage and corresponding current. Applications. The principle of heat transfer by radiation has been used in wide variety of areas like lasers, microwave ovens, radiation curing materials, solarism, mobile phones, MRI devices in the magnetic field, industrial heaters, sterilization of medical product, and so on.
Right, so this is an example of an actual experiment setup. Now, let's look this setup in the virtual lab. So this link is provided in your presentation also, as well as in the course content. So in the course content list, if you will click here, heat transfer by conduction, convection and radiation, you will be directed to virtual lab by Amrita University, right? So here we have seen heat transfer by conduction and convection, and this experiment is heat transfer by radiation. The next lecture, sorry, the next lecture that I am planning is on determination of Stephens constant, where we will verify the Stephens constant value, which is 5.67 into 10 to the power minus 8 watt per meter square Kelvin raised to 4. Right? Sorry. So go to the heat transfer by radiation part. Here the procedure and some theory is already discussed, that we have discussed in our class, is described here. Now, as you saw in the video itself, the procedure is very simple, that we have to first choose our material, determine its diameter, what diameter of specimen, what thickness to select, then select the chamber conditions. We have to switch on both the heaters for black body as well as the sample material, sample plate, allow the steady state to attain, and then note down the temperature. So here we have 3 temperature thermocouples provided for both black body and the test plate. average up the temperature of black bodies, and then you will get the average temperature, same average temperature of test material and the chamber temperature, and you have to put it into these equations to compute the emissivity. So it's fairly straightforward. Let's go to the simulator. In the simulator, you can select, see here different materials are provided. So let's see, we select and brass. You can vary its diameter and thickness. You can control the chamber temperature also. So let's say I keep chamber at a room temperature. Sorry. Room temperature of 20, let's say 26, it's okay. Then you can see here that this is how setup will look like. You have a chamber, 2 plates, each plate one black body, one the sample material, each plate with the 3 thermocouples to note down the temperature, and then you have a chamber temperature. Turn on the heaters for both the plates. Now since we want to compare the emissivity, both of the plates should be heated at the same rate. So heater knob for test plate as well as the black body plate will be same. So you should turn on to put at them at same value. Once you do that, we can start the experiment. Just power on the heater. You can show the results also. So for brass, emissivity is 0.68. Okay. Now allow an equilibrium to attain. Since it started heating, you can see the temperature is changing for both black body as well as the brass plate. So we have to wait for some time. Once the temperature fluctuations are gone, then we can conclude that steady state has attained and take the temperature readings at that point. So you can see here equilibrium is attained, and if you will look at temperature, you can vary the temperature between T1, T2, T3 through this knob. So T1, T2, T3 are connected to black body. So black body temperature is 572.57 Kelvin. Chamber temperature is T4, which was kept at room temperature, so 296 Kelvin. Then T5, T6 and T7 are connected to brass. Now we had provided same heating rate for test plate as well as the black plate, but you can see the temperature is different. The temperature for black body is 572 Kelvin, while for the brass it's 626, which is much higher. So from here itself you can draw the parallel that black body emits more radiation, that's why it has emitted much amount of energy, so its equilibrium temperature is lower, while the brass has a lesser emissivity, so it will emit less amount of radiation, thus its internal temperature is higher, right? So let's go for the calculation part. Here I have given the example of steel and aluminum. Just copy paste these tables. Now our material here is brass, right? Let's note down the temperature. 626.89. 626.89. Chamber temperature is T4, which is 296. Black body temperature is 572.57. Right. Let me just delete this. Yeah. .20 and 0.4. So the mean black body temperature is average of all three. Test plate temperature is average of T5 to T7, and then chamber temperature. So emissivity will be the formula that we have derived. We will use it. So here we are using this formula where emissivity of the black body is considered as 1. So it's just a temperature ratio between the black body and chamber, different divided by the plate temperature and the chamber temperature. So our emissivity value for brass comes around 0.679. If you will see in the simulator also, the emissivity is 0.68. Now here one thing is, although we have a facility to change the diameter and thickness for our sample plate, to change the chamber temperature, but emissivity is a material property, right? So it will remain same regardless of the dimension. So you can change the thickness, change the temperature, repeat the experiment at a different heating rate also, and what you will find that emissivity will come around same. So emissivity, it is a material property, right? Here, so the amount of radiation from a surface will depend upon the material as well as nature of the surface. So here material is same as well as nature of the surface. We are not altering the surface of any sample, we are just changing the dimension. So that will not affect your emissivity value. It might affect you to attain an equilibrium. So for a bigger dimension you might have to wait for a longer time for equilibrium to attain, but it won't affect the emissivity part. But for a same brass, let's say if you polish its surface, you make it very shiny, then its emissivity will go down because you have altered the surface property. That will affect its emission, okay? That will affect its emission ability, right? So be careful when you are doing this experiment, that although you have a facility to change this dimension, chamber temperature, heating rate, for same material with different dimension, emissivity will should come same. So the sample examples that I have given, I have considered them at different chamber temperature, different heating rate, even with the different dimension. And you can see for this one is for steel sorry, that emissivity is coming around same 0.85 in both cases, and same for aluminum, that emissivity is 0.77. So this was the experimental part. Now if you want to, one more thing here, since we don't have a hands-on on the real experiment, but if you will change, if you have a chance and if you can alter the surface property of a sample plate, then in that case you will note that emissivity value is changing. Okay, so that thing, if you get any chance, you can check it out, right? So this was the experiment related to heat transfer in radiation, where we computed the emissivity of different materials. Check this out. Check the virtual lab, do experiment with different materials, find their emissivity. We understood the theory behind the radiation, found out what is emissivity, what is black body, what are different types of emissivity, okay, and how it is useful. Now in the next experiment, what I am planning is to follow same idea, and then we can do one more radiation experiment, which will be black body radiation, to determine the Stephen-Boltzmann constant, right? So maybe in the next lecture what I will do, since we have already discussed the theory, I will directly start with the experimental explanation. We will look at the experiment idea, what we are going to do, how to perform that experiment, and then how to obtain the result and analyze them. Okay, so that is it for today's class. I will stop now, and then if any of you have doubt, we can discuss it out.